Good afternoon, fancy meat computers. How is everybody doing? I am soliciting comments on how your day has been going so far. I'm just going to speak nonsense until I hear my own voice to confirm it's working. And it's working. Excellent. Wonderful. Wonderful, wonderful, wonderful. Cool. Let me just see the Avenue feed. Let me see if I have any announcements to talk about today. Maybe I do. Maybe I don't. It's all a matter of chance. Yes. Nope. Okay. Nothing new. Good, good, good. Wonderful. So. Yeah. So, I suppose if there's nothing else pressing, we might as well press on. You are doomed by 3DB3. The databases course. You are doomed by linear algebra. Oh, yes. LinAlg is, yeah. It can be a little tough. It can be a little tough. But, you know, just keep muscling through, you know? It's like, just practice and practice and practice. Even though the practice, you don't feel like the practice is doing any good. And then in like a week, you'll be like, oh, wow, that practice actually did do me some good, didn't it? Yes. Stay positive. Stay strong. I believe in you. Just doomed in general? Aren't we all? Isn't that like the condition of existence? So, anyway, might as well press on. Not spend too much time complaining about courses other than this one. The assignment is chaotically written to hide information and is all interpretation. Interesting. So are we, like, talking chaotic good or chaotic evil here? Because, like, I feel like I'm kind of chaotic good in this class. Like, you know, we're doing traditional proofs, so it's like the algorithm for generating the proof is not necessarily laid out at your feet, but you know, you do have some flexibility in the manner of your presentation of your argument. So I would say that chaotic good, possibly chaotic neutral, but we'll see. I guess it all depends on how it's going to be marked, doesn't it? Anyway, so let's press on, shall we? Last time, remember, we actually I explained I explain things, so the chaos is welcome. Okay, good. As long as you guys aren't suffering needlessly, that's my goal. It's like we're gonna learn math, and we're going to try to remove the needless suffering, and focus specifically on the needful suffering. It is written from the point of view of a client who knows nothing about databases. I mean, good practice, but yeah. It's like they just got like some random business guy from the downtown. It's like, we need your help to make an assignment. It's like, I'm very busy, but I will give you some time. It's like, what would you want out of a database? It's like, da 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 da. Okay, that's a university assignment. Anyway, so defining our terms. In the previous section, we defined the small language of small. We defined the language of a small grammar using eBNF. That sentence seems wrong. We defined a small language using eBNF grammar is what that should say. I apologize. Let's examine some equivalent descriptions using the following. Defining terms inductively, defining terms using inference rules, and defining terms concretely. So, essentially, I'm going to sneeze. I think I'm going to sneeze. Headphone users, beware. It'll be back. No Kleenex around here, eh? Okay. Actually, yeah. If you give me like 1 second, I'll be right back. Okay. Sorry about that. So, remember, we defined our syntax for our untyped arithmetic expressions using eBNF. This was what we have. We have true, false, if then else, 0, successor, predecessor, and is 0. This is kind of your very small language that we're going to be exploring both in this topic and in topic 4. So, we're going to go through this and define our terms in a number of different ways to sort of explore the concepts a little bit. So eBNF is a component of UAE? No, eBNF is different. It's thank you. eBNF it's independent of like this is something that is written in eBNF. Like the difference between eBNF and the grammar is like the difference between the program and the language it's written in. eBNF is a meta notation for designing grammars. UAE is a grammar plus a syntax, or a grammar plus a semantic that forms a language. That door looks ominous. No, it's just a closet. It's just a closet. It's got a bunch of musical instruments in it. Anyway, so let's start off defining things inductively. So, we shall define the set of terms as follows. The set of terms is the smallest set T such that true, false, and 0 are a subset of T. If T1 is in T, then successor of T1, predecessor of T1, and is 0 T1 are all also, like, the set containing those elements is a subset of T. And if T1, T2, and T3 are all in T, then if T1, then T2, else T3 is a subset of T. Inductive definitions are ubiquitous in the study of programming languages. So this is kind of where we start to expand our brains and start to bring into our programming language descriptions the set theory stuff. The set theory stuff that we were doing in lecture 2, or topic 2. Consider this, right? The way that we currently have terms defined, a program is a term that is subdividable into more terms. So, by producing this description, we have produced the set of all possible programs, right? This is going to be a very important concept in this course. The idea that you have a set of all possible programs, right? And we're going to call these terms. So, you know, when you have an if statement and you have some term that's, you know, in the then branch of an if statement, the that term itself is its own program, which is separately, like, that can be separately evaluated from the if statement that contains it, right? So, doesn't that mean that any predicate on a term returns true? Doesn't that mean that any predicate on any term returns true? No. Nope. So, pred means predecessor, not predicate. We actually don't. So, the only one here that is a predicate in the sort of technical sense of it is 0. It's a predicate over 0 plus successive successors or predecessors, and all it does is it tells us whether or not T1 is 0 or not, and returns either a Boolean or a it returns either the true or the false value. So no, this does not mean that all predicates hold. Incidentally, going forward in the slides into topic 4, I realized that the textbook somewhat ambiguously uses very similar arrows for logical implication and the evaluation relation, which we're going to use quite extensively in the next topic. So I have taken the liberty of replacing, like, the single arrow with the double arrow wherever it had occurred throughout the slides. So if you downloaded the slides, get the new version from Avenue. Yes. Yeah, if this was a predicate, then yeah, but yeah, it isn't. If the first one is true, isn't it implied that is T1 So if this is true, then doesn't that imply this one is in there? So what we're doing, basically these guys did not exist before this statement in the inductive definition. According to the inductive definition, this is where these guys are being defined. They're being brought into existence in equation 3. So, inductive definitions are ubiquitous in the study of programming languages. The first clause gives us 3 simple expressions that are in T. The second and third clause give us 4 compound expressions that are in T. Yes. Yeah, what Pacific Cod has put into the chat is correct. Two-line arrow is implication. One-line arrow is evaluation. I would call it, because we're going to get into single-step semantics, and so single arrow is going to be one step of evaluation. So not producing the final output, producing one step towards the final output. Is T1 the one of true, false, or 0? Well, that's an interesting question. T1 can be anything that's in T. That means it can be true, false, or 0, or it could be any of these guys. So because this is an inductive definition, we can build it up from our base case, basically. So let's say we wanted, three successors applied, right? So you start off with 0. Because 0 is in T, we can say T1 is 0. Therefore, successor of 0 is in T. We can then set T1 equal to the successor of 0. That means that we can use successor of 0, and so on, and we can get as many of them as we want. It's an inductive definition, so think of this as being recursive. Yeah, think of it the best way to think of this is function application in the Haskell sense. Yeah, T1 is anything that's in T. Yep. So, the word smallest tells us that T has no elements except those required by the above clauses. Yeah. Fundamentally, this defines our set of terms as a set of trees. Although this grammar does not mention parentheses, we will use them for clarification. So Moonstar says, now technically this means you could have successor true, but that means nothing to you really. Yes, we're still just in the realm of syntax, right? We are not yet excluding nonsense, right? So successor of true is nonsense, but it's still valid under this form. We can have successor if T1, then T2, else T3. Yes, for any T1, T2, or T3 that are inside of the grammar. Yes. Yeah. Yes, absolutely. That's correct. That is correct, Daniel. Yep. Very true. So, yeah, T1, T2, or T3, these are all, any of these can be any legal construction. Any legal construction, including ones that contain several constructions. Remember, think recursively. So, I'm going to assume we've dwelt on this long enough. This is a slight rearrangement of the previous statements to use the rules of inference style rather than the inductive definition, the inductive style. So, we can also use rules of inference to represent our grammar, similarly to rules of natural deduction when used in the presentation of logical systems. So if you guys may remember your good friend modus ponens from your logic class, would have been represented possibly in a form looking like this. All this really means is the thing on the top is the premise, the things on the bottom are the conclusions. If there is not a line, that means it's an axiom. An axiom for a deductive system, the axiom is that which you take to be true without premises. It is just true. You define it to be true. So in this case, we're defining true, false, and 0 to be in T. We take the premise T is in T. T is in the set of terms. Then successor, predecessor, and is 0 are all in the set of terms. And if we have t1, t2, and t3 all in the set of terms, then if then else is also in the set of terms. Leibniz notation. Yes. So this is partially just to remind you that this notation exists. Kind of a funny story. I actually used inference rule notation in my original version of the slide. Like, we do some stuff with this in topic 4. In topic 4, we start to get a little closer to formal proofs, because once we have, like, you can set up rules of like, you can set up your semantics like a system of deduction, and then you can apply like formal, like this type of formal notation to it. I decided not to go with this notation, however. I decided to go with like the regular natural deduction, like the table form, because it just fits on the slide better. Like, the problem with this thing is, like, you can have one conclusion at the bottom, but like they have to branch out so wide at the sides that you lose the sides when you're trying to do it on a slide. So yeah, so that's the long and the short of it. Rules of inference are read. If we have established the premises above the line, we may derive the conclusion below the line. These are also referred to as antecedents and consequents. So, antecedent, consequent. In this type of formulation, the fact that T is the smallest set satisfying these rules is often not stated explicitly. Rules with no premises, such as true is an element of T, are often called axioms. Formally, the above inference rules are properly termed rule schemas. This is because they represent infinite sets of concrete rules via the inclusion of metavariables. So, because T can be any term, this guy right here actually represents an infinite number of rules, right? Like, if you're trying to apply this rule to T to get, like, the predecessor of T, you know, there are an infinite number of T's that could apply to, so there are an infinite number of predecessors applied to T that you can get. So these are rule schemas, rather than rules in the strict sense, but that's kind of just being pedantic about it. So, let's talk about terms concretely. So, the reason we're calling this concretely, this gives us, this formulation is not only defines all of the terms the same way that the previous ones did, but it also gives you a strategy for generating them. The previous, like in the inductive definition, like, we've defined all of this, but we don't really have like there's no way of going about generating all possible terms that's been suggested to us by this form. However, in this way, in the concrete form, there is a way of generating all of the terms. So let's go through it. For each natural number I, define the set S sub I as follows. For S sub 0, that is the empty set. For Si plus 1, you have true, false, and 0 in there, unioned with T successor T, predecessor T, and is 0T for T's in Si. So notice, this means that for every T in Si, we are including the successor, predecessor, and is 0 of it in the set of possible terms for Si plus 1. And we're doing the same thing for if then else. Notice that these guys do not have to be unique. They can all be true if you want. That would be if true, then true, else true. We're going to see a lot of things of that form coming up. Finally, the set of terms itself is equal to the union over all of these subsets. Cool. The previous description provides not only a definition for the language, but a mechanism for generating the terms of the language as well. S0 is empty. S1 contains only our constants. Later we'll call them values. S2 contains all terms built from constants. S3 contains all terms built from the terms of S2. S4 contains all terms built from the terms of S3, etc., etc., etc. Follow that through to infinity, and there you go. Yeah, so following the first two ways, you can create any term, but following the concrete way, you produce a set containing all possible terms. So we're going to have a proof that shows the equivalency between these two methods. But yeah, one way to think of it is like this is a description of a valid term. The concrete method is a way to generate the valid terms, right? So with the inductive definition, it would be easy enough to say something like, you know, I have this term, I need to decide whether or not it's in the language, right? So you could see, well, is it of the form if then else with T1, T2, and T3 being in the terms? And then you could say, well, is T1, T2, and T3 inside of this? And you could, you know, further analyze that all the way down until you hit things that are definitely in there, your, you know, concrete values, and then, you know, there you go. Is the body and range flipped in the previous slide? Oh, I've been flipping around. So this guy, body and range. So this guy, range. I'm not sure what that means, body and range. Can you be more specific? What do you mean by body and range? So the first definition is for any term of the language, but the second one is defining a specific type. No, it's still defining the terms of the language. It's still defining the terms of the language. It's just, you can think of it like the inductive definition is like a top-down definition, and the concrete one is like a bottom-up. Like, in one case, we analyze down to find out if something is a term. In the concrete sense, we build it up to find out if it's a term. But yeah, so we're going to now discuss the issue of whether or not the term T, the inductive definition, is in fact equivalent to the concrete definition. Oh, okay. So for you guys are used to having your set comprehensions reversed. This is the more classic form. I'm betting that I can just take a look in here and find set comprehensions that look the way that I'm doing them. But it doesn't matter. I can't show you that anyway because it's too blurry. This is, yeah, so generally speaking, this is like, I don't know if I've ever seen it the other way around. But, you know, then again, I didn't take the same courses that you took. So there you go. So, while it may be obvious to casual inspection that the inductive formulation of UAE is equivalent to the constructive formulation, a rigorous mathematician doesn't jump to such conclusions. Proving that the two formulations are equivalent will expose any inequivalencies, should they exist. I use other notation in assignment 1. Do I? Do I now? I don't think that I do. We'll see. Oh. Oh, right. So right here. Okay. But this is... Yeah, okay. It depends on what you're doing. In, Oh, that should have curly braces around it, too. So, for this, it's like the set... Like, it's establishing it as a tuple. Either way, it should be... Yeah, it should be, like... It should be obvious by the inclusion of the in operator, or, like, the for all, or existential quantifiers, what side of it is the bit that sets the domain. So... Hopefully, I'll try to be consistent from now on, though. So, such inequivalencies, if carried forward, may have disastrous consequences. So, if we have defined our language in, that's what you called traditional proof. Okay. So... Yeah, the problem is if you've defined things in two different ways, and those definitions are in theory equivalent, but you can't prove that they're equivalent, there's a problem with one of them, which means you don't understand your language sufficiently to be able to implement it, basically. As a demonstration of mathematical reasoning over these formulations, we will prove that the set of terms T inductively defined is equivalent to the set S, which has been constructively defined. So, let's prove T equals S. Here we go. Just as a reminder, we defined T as the smallest set satisfying the following conditions. This one, and this one, which I stated earlier. To prove that S is equal to T, it is sufficient to prove, number 1, that S satisfies all of the above conditions. So S should satisfy this, this, and this. And that for some S prime, which represents any set satisfying the above conditions, S must be a subset of that set. That is, S is always smaller than or equal to a generic set satisfying the conditions. So this is your way of proving that something is the smallest set satisfying some condition. Like, you know, for example, a closure property, perhaps. If you take... So the basic idea of the smallest set, you can think of it in terms of, does this set include junk, right? Does the set S contain any junk? Does it contain anything that's not laid out by T, right? We can construct a set that we simply define as satisfying these conditions, but we've sort of left it open that junk might be in it, right? If we prove that this set that might have junk in it is necessarily a superset of the set that we've defined, S, then we have proved that S is the smallest set. Because when we construct S prime, we are constructing it such that it may contain junk or it may not contain junk, right? So it may contain extra elements or it may not contain extra elements. If we prove, right, that S has to be a subset of it, it also has to be a subset of the case where S prime has no junk elements. Now, when I say subset, I mean subset equals. I don't mean strict subset. I mean S and S prime can be the same, but S prime has to be larger than or equal to the set S. Does that make sense to you guys? I know that's a little complicated. Before we get into it, I'd just like to wait to see if I've still got everybody on board. Okay. I think everybody's good then. So, we'll address the first part first, as is usual and proper. Let us consider our conditions one at a time. True, false, and zero. So S satisfies T. Yeah, that's what... Well, T is a set. S would satisfy the conditions that constructed T. Question. Isn't the size of the set that contains junk and the size of the set that has no junk the same, since they are both countably infinite? Yes, but is it a larger or a smaller infinity? So... your colleague points out, even if the set without junk is a subset of the set with junk. Yes, so... So, we've got some questions. So, one of your colleagues brings up the idea of, like, my inappropriate use of the term size. And... So, yes, it's, like, strictly speaking, technically true that the size of both of these sets would be infinity. I was explaining it in a kind of more intuitive fashion to try to, keep more people along with the class. Strictly speaking, S prime and S are both infinities, so, talking about which infinity is larger is, kind of like, you're starting to get into dicey semantic territory. I would say that me saying, like, my statement that S prime is larger is based on the intuition that something with more elements in it is larger, even if the cardinality of both is infinity, right? And, it's pretty clear that S plus junk data is going to be larger than just S, right? So, also, we kind of use the terminology smallest set satisfying this. So, like, although we are dealing with infinities, it is useful to think in terms of larger and smaller infinities, right? So, Mark... then what about some arbitrary superset of S? Rather, S must be a subset of S. Okay, yeah, I think you got it. How can S be countable infinite if it satisfies T, which has 3 base elements? Because you can have a theoretically infinite chain of, like, successors, right? There's no cap to the number of successor functions that you can apply to 0, so that makes it infinite. It's countably infinite because you have to, like, you can get there by counting, right? But, yeah. Anywho, continuing on. So, let us consider their cases one at a time. True, false, and 0 must be a subset of T. So, in our constructive definition, S1 contains only these constant terms, true, false, and 0, is equal to S1, which is a subset of S. So we may therefore conclude that this property holds for S. Next property, for T as an if T is an element, if the term T is an element of the set of terms, successor, predecessor, and is 0 of T must be in the set of terms. So, here's the proof. If T is an element of S, then it follows that T must be an element of some particular Si, because S is the union of all Si, right? All Si sets. Since there is no other possible origin for T, right? That it's when we construct S, it's the union of all subsets S0, S1, S2, etc. But no other elements have been included. So T must be in one of them. Given that one of the sets used to construct Si plus 1 is T, which is an element of Si, meaning that we have successor, predecessor, and is 0 of T, then these guys must be in Si plus 1, right? So, and since Si plus 1 is a subset of S, it follows that successor T, predecessor T, and is 0 T must be elements of S for any T. Because remember, I is going all the way to infinity, right? Make sense? Cool. So, the same argument, this argument here, may be applied to prove that T1, T2, and T3 are all elements of S as well. So, this is something that you're going to find with the proofs that I'm doing on the slides, is like, I could expand out the same argument for this guy and just say, you know, T1, T2, T3 instead of just T. But it's kind of like a waste of your time and mine, because it's like, just take this argument in your head, swap out, you know, swap this guy out for this guy, and you've basically, like, the same argument applies. This is a thing that you will often see in traditional proofs, where it's like, you know, you can apply the exact same argument to these different premises and get the result you want. So we're not gonna state it explicitly. We're just gonna say the same argument applies to this other case. And incidentally, it's okay if you do that in the assignments too. If an argument applies, just make sure that it actually does apply, right? Make sure that the reasoning is rigorous, and that when you make an assumption like that, it actually does apply. So, how did we arrive at S sub I plus 1 is a strict subset of S? Because it's in S, and it's, well, you got me. Mark P, you got me. That's not been demonstrated. That was just, like, I just know that's true, you know? Because, like, it's been constructed in such a way that each new element, like, each SI is going to contribute new members that didn't exist in any of the previous SIs, so each one is going to have unique elements it contributes to S, so each one, like, that means that it's a strict subset rather than a subset, because in order for it to be a subset and not a strict subset, you would have to have, like, one layer at which, like, everything is included. Well, which, you know, can't possibly be the case because it's infinity. There's always another set. Although, perhaps according to our definition, the final one contains all of the previous. Maybe the final one that doesn't exist contains all previous ones. Well, at any rate, you caught me. That should probably be subset equals. What happens if you take the union of a set and another set which contains duplicate elements? Does it ignore the duplicates? Yes! That is a property of union, the union operator. Yes. There's a limited number of stuff in each S. Right, yes. So, basically, like, so long as I isn't actually infinity, the number of elements in Si is finite. Right? I think. But yeah. It depends on what what Si is. Right? If you follow it to the limit at infinity, you'll get an infinite number. Union of sets doesn't replicate duplicates. Bags do, however. Yes. Thank you, Pacific Cod. A fine fish. So we've demonstrated that S follows these three, right? These three properties are true in our constructive definition. We have one property remaining to demonstrate, and that is whether or not S is the smallest set of terms that satisfy those conditions. So we will proceed along the line of reasoning that I previously stated. Let's suppose that some set S prime satisfies the conditions set out in our inductive definition of T. We are defining S prime so as to satisfy those conditions. We will start by proving via complete induction that Si is a subset of S. Or S prime, sorry. It will then be trivial to show that S is a subset of S prime. So, if each Si is a subset of S prime, then the union of all Si's will also be a subset of S prime. So let's do an inductive. Let's do induction. Premise: for all j less than I, assume Sj is a subset of S. That's our induction hypothesis. So let's do a case analysis. Case: I is equal to 0. If I is equal to 0, then S at 0 is the empty set. And the empty set is trivially an element of every set. So we have our base case. Otherwise, I is equal to j plus 1 for some j which is an element of n. Right? So j is 1. So during our inductive step, we're going to do it for I minus 1, which is j. We're going to call j I minus 1. It's phrased a little weirdly, but that's all right. Let T be an element of Sj plus 1, that is to say Si. Sj plus 1 is constructed from 3 smaller sets, so T has 3 possible origins. T is either an element of true, false, or 0, or it's an element of successor, predecessor, or is 0 of T1, or it is if T1, then T2, else T3, where T1, T2, and T3 are all elements of Sj. Right? Makes sense? T has to have one of these forms. So we're going to proceed by case analysis. Following from this, for equation 10, that is to say, this guy, we know that T is an element of S prime via equation 5 above. Equation 5 right here. It satisfies this property right? S must satisfy this property, so we can say that this must be true, right? S prime has to satisfy, like, this must be true because S prime has to satisfy this property by construction, right? Similarly, for equation 11, we know that T is an element of S prime via equation 6, and the fact that T1 is an element of S prime via the induction hypothesis. So for this guy, we satisfy, let's just talk about successor of T, right? So we know that the successor of T1 is in there, and we know from here. So we have this property. This property is true. Successor of T1 is an element of this set so long as T1 was also in the set. Now, T1 must be in the set because we have established that via the induction hypothesis, right? Remember, our induction hypothesis is we're assuming that Sj is a sub-element, right? So, there we go. And so we get there via the induction hypothesis. For equation 12, basically it's the same argument, but we have to apply the induction hypothesis to T1, T2, and T3, which fortunately we can because we've assumed that everything that's in Sj or lower is already in this set, right? So there you go. Since every possible T is an element of T prime, it follows that Si, which is the union... which Si is the union of every T we just discussed, is also a subset of S prime, right? If everything... So this whole proof hinges on the property that if X, Y, and Z are all subsets of a prime of a set A, X, Y, and Z are all a subset of A individually, the union of all of those is also a subset of A. This is a property of union. It's like you do not if everything was already in A, you do not include anything that's not in A by taking the union of everything that's in by taking the union of things that are in A, right? So that's like that's the property that this whole proof has been constructed around. So by similar argument, sorry, did I do this one? Since every possible T is an element of S prime, it follows that Si... Yeah, I did that one. By a similar argument, since each Si is a subset of S prime, and S is the union of all Si, it follows that S is a subset of S prime. Therefore, any arbitrarily constructed set S prime satisfying the conditions of T... for any arbitrarily constructed set S prime satisfying the conditions of T, the S obtained by our constructive definition is at most as big as S prime. Therefore, S is the smallest set for which the conditions hold. And that's time. Wow, how perfect is that? So, if you have any questions, please put those in the chat now. If you do not, we will reconvene on Monday. Or wait, Tuesday? I think it's Tuesday for this class. Yeah, definitely Tuesday. Tuesday is 3 lecture day for me. Yeah. Any questions? And Joe says QED. Quod erat demonstrandum. Can I hit on the second bullet again? Lol. Alright. Hitting this guy again. So, since every possible t is an element of S prime, right? We've established all of these guys have to be an S prime because S prime has the properties that are given in the inductive definition, right? It follows that Si, which is the union of all of the t's, is also a subset of S prime, which is, that's that thing I was saying, where if X, Y, and Z are all subsets of the set A, then the union of those has to also be a subset of A, right? That's a property of union. This completes the inductive subproof. So there you go. And then you make a similar argument over the union property the same union property here gives you the result that S is a sub-element of S prime because S is just the union of all of the SIs. But yeah, so there you go. Second bullet. Can there be a proof via weak induction where we didn't use the induction hypothesis? It's very difficult to answer a question like, does this exist or not? Because in mathematics, it's like every single time I answer the question, does this exist, in the negative, like someone somewhere is going to find it for me. But weak induction. So weak induction as opposed to complete induction, right? So I don't think that you can use weak induction here. Like you would need a secondary proof that like Sj contains all possible terms that have been made so far, because like when we're saying that T1 is an element of T here, like it can be. If you map that onto the constructive definition, it could be from any SI that it comes, right? It doesn't have to be from, the most recent. So if you only use weak induction, you would basically have to derive complete induction anyway to hit those cases. So I think that strong induction is the one that you want in this case. I don't think a weak induction case can be made in this case. But then again, every time I say something, someone's gonna find a case where I'm wrong. So there you go. When are office hours, and could I hypothetically show up to go over all this again? Yeah. So office hours are Thursdays from 1:30 to 3:30. I'm doing them dual, so if you show up in person, I will be in the room. That's ITB 102. And if you show up to the MS Teams, I will have a call going on in the same room. So yeah, it's last time my mic wasn't working, but so I'll try to fix that for this time. But yeah. Yeah. So yeah, all induction can be theoretically done with weak induction and vice versa, but sometimes it's really hard to do it with just one. So one of the things that you should try, one of the things that's true is that basically all of the forms of induction that we're going to be using throughout the course are interderivable. That is to say, you can arrive at complete induction from weak induction and vice versa, right? The trick is matching the form of induction you're using to the problem at hand, because by matching those up, you can save yourself a hell of a lot of work. Basically, you can save yourself the trouble In our example, in this example, you save yourself the trouble of having to derive complete induction at the same time as doing your proof if you just start using complete induction. Should you use this method in proving closures? Well, given that one of the properties of the closure is that the closure is the smallest set that completes the reflexive or the transitive property, I would say that this is a pretty good, this is, like, I just showed you how to prove a set is the smallest set, so you might find that useful. Just saying. Yeah. No, I mean, if I can prove something without induction, the induction hypothesis, can you do that? Yeah, like, if you have a proof that doesn't use induction, that's fine. Most of, like, I'm gonna go out on a limb and say, like, probably most of the proofs that we're gonna do in this entire class are gonna use induction. So, can you not use induction? I guess, if you can figure out how to do it. We'll be following your logic, though. Make sure your argument is rigorous. But yeah, let me put it to you this way. I kind of take the same. I'll be sure to tell the TAs this as well. I take the same kind of approach to proofs in this class that I took with programs in 1MD3. It's like, you should have enough freedom to be able to make the proof how you think the proof should be made, and our job is to understand what you've written and, you know, mark it for its veracity. I'm not trying to constrain people to, you know, only write proofs in certain forms. Like, you should understand the properties going on. You should be able to make the argument, like, from the properties. I'm not going to be, like, enforcing a lot of stylistic rules when it comes to your proofs, because you should be, you know, you guys are kind of big enough and ugly enough to be able to come up with your own style for doing this at this point, I should think. So, can't have induction without induction hypothesis, so it's definitely possible to prove something without using induction. Oh, yeah, like, yes. Yeah, it's definitely possible to prove things without induction. You know, when you guys did natural deduction, you know, it's like, generally speaking, proofs are divided into two camps, right? You have the inductive camp, which is what we've been doing so far, and you have the deductive camp. So in the deductive camp, you don't use the induction hypothesis, and, you know, that's, you know, if you wanted to prove modus ponens from, you know, the, you know, axioms of propositional logic, you would do it via deduction. Induction, on the other hand, if you are dealing with things that have a recursive structure, if you're not using induction, you're probably doing it wrong, right? Induction is made for things that have an inductive or a recursive structure. Like, we friggin' called the way that we wrote our axioms, like, we called our properties the inductive definition, so that suggests that you use induction for proofs. But, yeah, if you can figure out a way of not using induction on a recursive infinite structure, then, you know, by all means, if you want to beat your brain against that particular brick wall, I'm not going to stop you. It's like, it's like in Dark Souls, if you're fighting the Tauros demon, using the induction hypothesis is like realizing that you can get up onto the turret behind him and then, like, jump stab him. That's what the induction hypothesis is. So, the statement is this statement because in the induction hypothesis has the assumption, so induction is only as good as its assumption. So, No, it's like, So, yeah, it's definitely true that the induction hypothesis is only as good as its assumption. However, like, normally the induction hypothesis will be given to you in the question. Right? Like, in this case, the induction hypothesis was, it was like it was the thing we're trying to prove, right? It was this holds, right? So, we're given this. We assume that holds for previous things. So in theory, like, I don't think that you should have to come up with your own induction hypothesis. If you're casting about for the induction hypothesis itself, you should probably reread the question. So, for example, if I get something like P plus Q is greater than P, so this is, I believe, a common sense, if, of course, Q is greater than 0. Well, I mean, is it common sense, though? Right? Like, your analogy works if you're dealing with, like, the natural numbers there, Riddle. But if you're dealing with, like, if your ordering relation there has exotic properties, then that might not necessarily be the case, right? And it also really strongly depends on what plus means, right? In your example, I'm taking plus to imply that P and Q are, like, numbers, like natural numbers or integers or something. But if you consider P and Q to be related by some operator other than addition, like, say they're the union or something, right? Or in the context of this class, imagine that they're related by the evaluation relation that we're going to be talking about next week. If P evaluates to Q, and basically, well, it doesn't really make a lot of sense, right? Because, like, if you're talking about Q being, ordered over P, like, what does ordering even mean for it, right? So, but yeah, use induction, but never explicitly use the induction hypothesis. Hey, you gotta state that explicitly, Moonstar. When we modify proof to use complete induction, only the induction hypothesis is changed, right? I feel like for the Fibonacci sequence in A1, not much can be changed in terms of the proof. Yes. Yeah, it's kind of like, yeah. So, in A1, not the text, in A1, let me read that again. Yeah, so question 4 and 5, right? Yeah, it's, the proof doesn't change a whole lot. However, like, I would even say it's a trivial change. That's why question 4 is worth 3 points and question 5 is worth, question 4 is worth 3 points and question 5 is worth 2 points. It's a trivial change versus question 4. But it still needs to be explicitly stated, right? But yeah. So yeah, like, well, it's like, yeah, like, the proof that you've given, Meridal, on, like, P plus Q is greater than P if Q is greater than 0. Yeah, that's like, that's a perfectly valid thing to prove over natural numbers that doesn't require induction. All it requires is the properties of the total ordering over the natural numbers and the properties of addition, in that a number cannot be less than like two numbers, like the sum of two numbers is always greater than the two numbers, right? But yeah. Question 5 is an easier proof than 4 because you didn't have to talk about the identity of addition. You could use isotonicity. Ha! I guess so. Anyway, so I've rattled... Wow, it's quite late. Take her easy, folks. Have a nice weekend. We'll see each other again on Tuesday. It's okay that we took this long because we were talking about math. This will be useful to people who are watching the stream afterwards. Take her easy, folks.